Okay, students, let's try this again. Chapter 8, Equilibrium and Elasticity. Look at torque and static equilibrium. Now, we've already talked a little bit about static and dynamic equilibrium, so we're going to revisit the topic again. Anytime you have a net force of 0 acting on an object, it's said to be at static equilibrium. Now, don't confuse it with dynamic. Dynamic is when an object is moving and it has a constant force applied to it. It's at dynamic equilibrium, okay? All right. Okay. All right. So, when we look at torque and static equilibrium, we have to not only look at forces, but we have to look at torque. Okay, and just as with when the net torque is 0, we have static equilibrium, just like when the net force is 0. Okay, and so we need to remember that regardless of whether it's moving in the X or Y or whether we're looking at torque, if the sum of those forces in the X and Y or the sum of all the torques equals 0, then there is no net torque, and therefore we are at static equilibrium. Now, which object is at static equilibrium? Well, it'd have to be D. Notice these two forces are pulling to the right, and the vectors, if you add both of them up, will equal that one in the opposite direction. So it's at static equilibrium. Now, for an object in static equilibrium, the net torque about every point must be 0. Okay? So the net torque here, the net torque here, the net torque there, okay, has to be 0. Okay? Notice it said about every point. Now, you can pick whichever points you want to calculate. Doesn't matter. Okay? Static equilibrium problems, again, this is just a kind of a review of how to set them up. Of course, as with all physics problems, you need to draw and then pick your pivot axis, determine the torque about the pivot, determine the sign, and then, of course, solve it. Okay? Now, I was supposed to have deleted that. There we go. All right, stability and balance. Now, when we look at extended objects, they have what we call a support base. In this case, we have the wheels. Okay. Now, one thing about keeping an object stable, keeping it from tipping over like a car or a truck, you want to keep it as low to the ground as possible, and you want to make it as wide as possible, because when you have a wider support base and a lower center of gravity, that increases stability tremendously. Now, I'm sure everyone probably knew that. You thought, well, yeah, I knew that because I used to have a Jeep and I had to be careful in it because it would turn over pretty easy when I was going around the curve at a pretty good rate of speed. Well, that is true. Some of the older model Jeeps, and especially military Jeeps, the older models, sometimes had a tendency to want to flip if you're going a little bit too fast around the curve. Okay, so what they do to get around that, they widen the base of the vehicle. All right, now, as long as you keep center of gravity over the base, then gravity will, as it's moving, will rotate it back towards the equilibrium position. However, if it gets outside of its base, then guess what it's going to do? It's going to turn over. Notice right here how they're showing you the vehicle. Okay, center of gravity is within. Ooh, that's right at the threshold. Okay. Notice that it is complete, it's straight in line with the pivot point, okay? Once the center of gravity gets beyond the pivot point, well, it's too late. It's going to come over, okay? If you can get it right there, you see these stunt car drivers drive up on two wheels. Well, that's what they're doing, okay? All right. Springs and Hooke's Law. Now, Hooke's Law, to me, I think, is probably one of the easiest things to teach. They show you a golf club there. That's a good example of Hooke's Law. Notice how when the club face hits the golf ball, notice how the golf ball is deformed. Well, why does the golf ball not look like that after you've hit it and then you go pick it up? Well, because it has what's called a restoring force, okay? So the restoring force is the force that basically puts the object back to a state of equilibrium or position of equilibrium, okay? Now, we call things that are like this elastic. You know, we think about springs and rubber bands. They are elastic. Now, one thing about rubber bands, though, even though they are elastic, you can stretch a rubber band and it will not go back to its original shape like a spring will, okay? Rubber bands have what's called rheostasis. And you know, as the more you stretch them, the worse it gets. And eventually they'll break, okay? All right, now, so what do we need to remember about Hooke's Law? It's very simple. Always remember that the spring force now, is always going to be directly proportional to the displacement of the end of the spring, okay? And always remember, too, that restoring force, the restoring force is always in the opposite direction of the displacement, okay? Notice they compress the spring here. Well, which way is the restoring force? It's in the opposite direction. They stretch the spring here, okay? Notice they stretch it that way. Which way is the restoring force? Opposite direction, okay? So it's always going to be in the opposite direction. Now, I did this past semester with my calculus-based folks, and you know, when you plot spring force versus displacement, you get a really pretty nice slope. You actually should get this, okay? Force and delta x. You should get something like that, okay? Because it actually is a negative slope, okay? And again, that doesn't mean that the constant is negative. It just means that there's a restoring force, okay? So we have a linear relationship here, and here is Hooke's Law, okay? The spring force, restoring force, is equal to the spring constant times the change in displacement. Now, in actuality, this is how we should write Hooke's Law. You see that little negative there? That means that the restoring force is in the opposite direction. Has nothing to do with the K constant, okay? The K constant is always positive. The spring constant is always positive, okay? The negative just tells us that it's in the opposite direction, okay? Okay, there's another equation to put on your formula card. What about if we got something vertical? Same thing, just change it from x to y, okay? So make sure you write down Hooke's Law on your formula card. All right, which has the greatest restoring force? Well, I hope you say A. Absolutely, okay? Stretching and compressing materials. Now, I don't know if you've ever noticed this, but when you pull on something that's very rigid, have you ever noticed that you can pull on or try to bend a steel rod? Have you ever noticed how even though it's very rigid, it seems like there's a little bit of elasticity to it, that it will stretch and come back? Well, that's because it is, okay? Now, when you look at steel, here they're talking about steel, you don't see, under normal circumstances, a whole lot of change in the dimensions of the material. You don't want it to, okay? Listen, you don't want that steel beam when those cars and trucks goes across that bridge to be changing. You don't want them to be very elastic, okay? You want them to be very rigid, okay? Because, you know, rubber bands and some other metals are a lot more elastic in nature than steel, okay, or cast iron. So we don't want it to be, if we're going to be carrying a heavy load, we're going to need some rigidity there. Okay, so we can calculate the actual spring constant, the stretching constant or spring constant of a rod with this equation here. Now, that is area. L is the actual length, total length. Okay. And this right here is called Young's modulus. And Young's modulus is based on the material from which the rod or the steel I-beam or whatever it is we're looking at is made. Okay. So we can actually find the spring constant there. Now, Young's modulus has a value of meters, well, shoot. I think it's meters, yeah, 1 over meters. I believe that's right. Is that right? All right, which bars A and B are attached to a wall to the left and pull equal force to the right? Bar B is twice the radius. It's stretched half as far as bar A, which has a larger value of Young's modulus. Well, it'd have to be YA, okay? And here they show you why. Now, so, yes, Newton's meter squared. I knew I was leaving off Newton's. Lord help me. I'm not using my brain too well today because spring constant, Hooke's law, is newtons per meter, okay? Newtons per meter, okay? All right, so notice that cast iron has a very high Young's modulus. Steel does too. Notice as we come down, it gets less and less and less, okay? In other words, the rigidity really drops off, doesn't it? Now, so the restoring force can be written in terms of the change in length. So what we can do then is we can actually find the force required or the force produced when you have a material, the area of the material, the length, and its change in length. You plug in the Young's modulus for that material, and we can actually find and I don't know why they didn't say restoring force here. We'll just put spring right there. For this, you can find the restoring force for this particular material, like a rebar that goes in concrete, okay? So what we can do then is we can rearrange it just a little bit, and we could look at something called stress and strain of the material. Here's the stress, and here is the strain, okay? Stress many times is referred to as the tensile strength, okay? The tensile strength of the material, okay? So stress is referred to as the tensile strength or tensile stress. And then, of course, strain is just strain, okay? Can be more like compression, okay? This is stretching and that's compressing, okay? Stretching and compressing, okay? So, now where did they get this equation? Well, they got it from right there, okay? They moved the area down here and then it left what? Y delta L over L, okay? So we can find the tensile stress this way. And the unit of stress is newtons per meter squared, okay? Newtons per meter squared. All right? Okay. Hope that helps.